Hi, everyone. We're going to work on Coulombs law today, but specifically in the electric field form, and I'm going to specifically talk about it in differential form so that we can actually use it as a integration. And I'm going to derive a vector form of it. When we're normally doing just discrete charges, you could, in principle, always make up a vector form, but in practice, it's almost never that helpful to do it that way unless you're writing computer code for it. But in terms of actually integrating, you sort of need the vector components, or you have to play really cute little mathematical tricks to pull it off. So I'm going to go ahead and show you Coulomb's law, both the force version, and then how you get from that the electric field version, and then how you get from that the integral / differential version. And then I'll go into deriving the actual mathematical vector form. So let's turn my document cam on. So Coulomb's law is the force is equal to Q1 Q2 over 4 pi epsilon naught r squared. And we know that the force is either repulsive or attractive. It's repulsive when the two charges are the same, and it's attractive when the two charges are different. And you can tell, of course, it's equal to the product or proportional to the product of the charges and inversely proportional to the square of the distance between them. Sometimes people don't use the 1 over 4 pi epsilon naught factor, and they'll say K Q1 Q2 over r squared, and that's fine as well. But the other aspect of Coulomb's law is that the force, being a force, is a vector quantity and needs a direction, and Coulomb specified that the direction is in fact along the line connecting the center of charge of these two charges, or ideally you'd imagine the two charges are actually point charges, and then the direction of force would be along the line connecting them. So we could easily, of course, do that. The problem with this is that it had that old action at a distance thing. It was as if, the proton inside of a hydrogen atom was reaching across a small distance of space and pulling on the electron, even though they had no physical attachment, no strings or anything like that. And this bothered people just like it bothered Newton and people that followed Newton about gravity having that action at a distance. But in both cases, but it actually stuck a little bit better with this one. In both cases, they actually imagined and said that a charge, let's say Q1, actually distorted the space around itself. And then Q2 came in and was actually affected by that distortion of space. And they named that distortion of space a field. And a field really is just an assignment of some quantity. For instance, if it's a temperature field, you'd assign it a temperature to every point in space, x1, y1, z1. Same thing with the electric field, except in that case, you'd actually, since electric field's a vector, you'd have to assign it a magnitude and direction at every point in space, and every point in space would be, again, x1, y1, z1, x2, y2, z2, but in fact, it's an infinity of points, so it's not really correct to sort of subscript that with a 1 as if they're discrete counting numbers. So that's what an actual field is. They're vector fields like the electric field, or you can even call it a force field. And there's also scalar fields like the temperature field or a pressure field, which would be like a vector field, all sorts of good stuff like that. So when we introduced the actual electric field, what we did was we said the electric field, and maybe we'll say this is the electric field due to charge 1, would in fact be equal to K times Q1 Q2 over r squared, but we want it to take out the effect that Q2 had on it, so we divided by Q2. But Q2 itself really has the ability to make its own distortion of space. So in principle, when we do this electric field definition, we should really define it in terms of a limit as Q2 approaches 0. In other words, we want to consider the case where Q2 has as little effect on the field as possible. So ultimately what we get is the electric field is equal to K Q over r squared, and that's the electric field caused by Q. Again, this is just a magnitude, so we actually have to define a direction. If you want to consider an infinitesimal little small amounts of charge dq, then we can convert that to dE is equal to k dq over r squared, where again r squared is the distance between the dq and the point at which you wish to know the electric field. So let's imagine this for a second. I'm going to create an XYZ coordinate system. So this will be X, this will be Y, this will be Z. I did make this a right-handed coordinate system, but it didn't really matter too much in this case because I'm just going to work with some vectors. But let's imagine that we have a vector that points to the point in space that you wish to know the electric field, and we have another vector that points to the actual charge dq. So let's say the charge dq is here. Then this vector that points to it is r sub dq. Now, if we wish to know the electric field caused by dq at some other point, let's say right here, P, then we'd have to consider the vector rp as well. Okay. What we do know is, just like in Coulomb's law for the force, we know that the electric field has to point along the line connecting the charge and the individual point, because in the case of the original electric field equation, the original electric force equation, it acted along the line connecting the two charges. Well, this isn't very relevant until you think about putting a charge there and seeing what kind of force would come out. So yeah, it's going to be along this line connecting the two, which means this line. Now I'm drawing it in 3 dimensions, so you got to remember this one could be way out in front of the XY plane. This one could in fact be back behind the YZ plane, and this one could be back behind the DZ plane, the YZ plane, and that's all well and good. Now what I want you to do is I would like you to think of all the different types of mathematical operations you can apply to RP, or to RDQ, or to RP and RDQ. What are all the different mathematical operations you could apply to either one of those vectors or both of those vectors at the same time in such a way that you could get a vector that points along this line somewhere? Now, this is a place where you'd want to pause the video and try to think about it. I give my students usually a good 10 seconds to think about it, and then they start sort of going through the list, and ultimately some of them even get it. So like I said, this would be a good place for you to pause it and try to think about it yourself a little bit. I'll just ask you a couple leading questions like, what are the operations you can apply to a single vector? Well, you can take a single vector and you can multiply it by a scalar. You can take a dot product with a single vector with another vector. You can take a cross product with a vector and another vector. You can also take a sum of 2 vectors, or you can take a difference of 2 vectors. And you can even add 2 vectors and then multiply them by a scalar, all sorts of stuff like that. So you're thinking through those and try to come up with any operation on one of them, the other of them, or both of them that gives you a vector that points somewhere along this line. Either direction doesn't matter. So pause it and think about that. I'm going to go ahead and start discussing what the actual answer is. So it turns out if you wish to know the electric field at this point here due to this charge here, if the dq is positive, then it's going to point in the direction that a positive charge would be pushed. So in other words, the electric field is defined to be the position or the direction, the electric field's direction is defined to be the direction in which a positive charge would be compelled to move. So if I put another positive charge here and assume dq is positive, then I would expect the charge or the electric field to push along this way. So we would say along this line right here is the direction DE, and it should be in fact along that direction, because if we actually have a negative differential charge, then that will come out, and when you multiply a DE by a negative, you end up getting it pointing in the opposite direction. So everything just works out really nicely. So it should be along that line, and I would argue that you can subtract the 2 vectors. Okay, I'd be right because I'm telling you this. But it's a matter of then thinking about, do I want to do RP minus RDQ, or do I want to do RDQ minus RP? This is another place where you might want to pause the video and try to think that answer out yourself. I'm going to go ahead and tell the answer. So when you wish to subtract 2 vectors, you use the old thing that we learned from algebra, that A minus B is defined to be A plus the opposite of B. So if we actually make this a vector equation, which is actually true, of course, vector algebra is an algebra, so it obeys this rule. The opposite of B in terms of vectors means a vector pointing in the opposite direction. So when I want to subtract two vectors, I actually take the first one and leave it B. So I definitely want this one pointing directly to there, because that's the point that I wish it to be. If I flip this one around, that's what the equivalent of multiplying by a -1 would be, then I would have a vector, two vectors that were head to tail, the tail of the first one starting here, the head of the first one here, and then the tail of the second one here, and the tail of the first, or the head of the first one, or second one there. So that would in fact give me the direction I want. So in fact, the direction of DE is given by RP minus RDQ. Okay, so that's actually our direction. So I'm going to now take this magnitude and incorporate that. So I'm going to say it's K. And again, I don't really like working with K. I'd rather write 1/4 pi epsilon naught, but right now it's really much more convenient to write it this way. So I'm going to say dq over r squared times rp minus r dq. And this is not right yet. It's not actually correct. You all might want to pause the video and try to think about what's wrong with it. I will tell you that the size is jacked up now. So you might want to pause it, think a little bit about it, and I'm now going to explain it. So it turns out if I multiply k dq over r squared, which is the right magnitude of dE, by the vector rp minus rdq, then I've actually increased the magnitude by the very magnitude of rp minus rdq. So that's a problem. But we also should look, does this RP minus RDQ, does it have anything to do with this R down here? In fact, it does. This R right here is in fact the magnitude of that. So just for a second, I'm going to write DE is equal to K DQ over magnitude of RP minus RDQ squared times RP minus RDQ. Again, this is not correct. This one isn't, and this one isn't, okay? Not yet. The problem is I've still got the magnitude of the electric field jacked up because I have an additional amount of quantity, the magnitude of this, being multiplied by it. So if the electric field is too big by a factor of the magnitude of this, how do I correct it? Again, here's a nice place for you to pause it and try to answer that question. So the way you correct it can be thought of two ways. Is one, I can just think about, well, the magnitude of the electric field is too high by a factor of the magnitude of RP minus RDQ, so I just divide the DE by the magnitude of RP minus RDQ, and that works fine. That is actually exactly right. But another way of thinking about it is, maybe I shouldn't have multiplied by this from the get-go. Maybe I should have taken this vector, found a unit vector that points in the direction that this one does, and then multiplied that by it, and that would be fine too, because it turns out the unit vector, or any unit vector, is in fact the vector that you want divided by its magnitude. So really, if I want it correct, I want to write DE is equal to K DQ over RP minus RDQ cubed now, because notice when I'm divide by this, I've already got one of those down there, so that becomes RP minus RDQ cubed instead of squared, times RP minus RDQ. And I got to tell you something else about this. In physics, we're often a little fast and loose with our mathematics. So the fact that this being after the DQ might make a mathematician think that this isn't part of the integral. It is definitely 100% part of the integral, as is this. So just keep that in mind when you actually go to integrate a problem. You actually have to integrate this part as well. So that's a good way of thinking about it. Now we actually have the formula for the electric field as a vector formula. using a differential charge element. So we can actually use that to solve a physics problem. So let me give you a slight example or a simple example, and then show you how you'd actually use this formula to work that out. So let's imagine a infinite line of charge, and let's say this is going to be the z-axis, and this is going to be the y-axis. And I'll imagine a line of charge that's infinitely long. In other words, it goes on for infinity this way, and it goes on for infinity this way. Okay? And I'd like to come out here a distance, let's say, let's just call this distance r. And this is my point P. Okay? I would like to now set up this integral. I'm not going to do the whole integral, that's for a later video, but I want to set up this integral. So what I would do is I would break this line of charge up into infinitesimal charge amounts, and I usually try to stick in the first quadrant or on the positive axes if I'm going to be on an axis. So right here, I would define this little distance right here, from here to here. I'd call that distance dz. Okay. And then the rule is there's several charge densities that we use in electrostatics and electrodynamics, and those are lambda, which is dq over dl. There's sigma, which is dq over dA, and there's rho, which is dq over dV. So lambda is a charge per unit length, sigma is a charge per unit area, and rho is a charge per unit volume. And in fact, from that, if you sort of integrate it and imagine these to be constants, then you get simple formulas like dq equals lambda dl, or dq equals sigma dA, or dq equals rho dV. And that's fine. In practice, though, these might actually be functions of r or theta or phi or x or y or z or something like that, in which case you actually have to compute the integral, so it's a little more complicated. So I'm just going to leave that there, and I think you can tell that this one should be a charge per unit length. And that would be the typical problem they give you. What if the charge per unit length on an infinite amount of charge was 1 Coulomb per meter? Now calculate the electric field at a distance r away from the central rotational or symmetry axis of the charge distribution. Now when you do that, because it's infinitely long, it really doesn't matter where it is. You sort of picture it as the center no matter what, because it's going to go infinitely far both ways. So that tells us this little unit of this chunk of material has a charge dq given by lambda dl. Now, if I said that charge per unit length was 1 Coulomb per meter, then lambda is clearly a constant. Or if I tell you by that the charge density is constant, you just call it lambda and treat it as a constant. So that's all well and good. So now I have dq. Well, the things I need in this new formula we figured out is a vector pointing to P and a vector pointing to dq, the difference of those vectors and the magnitude of that vector, of that difference vector. Okay. So let's start filling those out, and that will be basically 90% of the problem. In fact, I normally give my students somewhere between 90 and 95% of the credit for a problem if they set this up properly and get the integral set up properly, but still can't do the integral. So first off, RP is this vector right here. And you should know that one way to find a vector is you pretend that the points, x, y, z, for instance, the final point, which would be x final, y final, z final, and the initial point, x initial, comma, y initial, comma, z initial. If you just subtract those coordinates, then the answers in each little slot is the component. So in this case, this one only has a y component. That y component is r, and this is all at the origin. So it has nothing but 0, 0, 0. So this point is 0, 0, 0. This point is 0, R, 0. So if I subtract that, I just get RP is equal to R J hat. Easy peasy. Now, if I wish to know r dq, that's going to be this little vector right here. So this is r dq. And since it's along the z-axis, I'm going to assume that is a distance z. Okay? So this point has the point, the origin, 0, 0, 0. This point has the point 0, 0, z. So subtracting those, I can say that r dq is in fact equal to z k hat. So I've got rp and I've got r dq now. And in fact, if I wanted to do rp minus r dq, then that would be a third vector going from here to here, and that is rp minus r dq. I think you can tell from this drawing that this leg has a length r, this leg has a length z, so this has a length of the square root of r squared plus z squared, which is in fact the magnitude of rp minus r dq. So it's the square root of r squared plus z squared. Okay. And finally, the actual vector itself, rp minus r dq, is equal to, this is the easiest math in the world because there's no like components, if you will. This component is in the j direction, this one's in the k direction. So I just get r j hat minus z k hat. That is the rp minus r dq. So now I've got all the parts. I just plug this into there. I'd plug this into there. Of course, it's going to be cubed, so it'll be to the 3/2 power. I'd even plug in dq. I'd plug in lambda dl for that, and now I have everything. It's just a matter of integrating it, but we'll do that on another problem. That's it. I hope it helps.